To understand a CCR attack, we must first understand the basics of a data surface theory. A data surface is essentially a file or a part of a file that is created by performing XOR operation on the decompressed fragments. In the case of a fission core of type n+2, where n is equal to 2, we will have 4 dimensions, so 4 different colors. And the smallest possible data surface we can produce by this core is made up of 2 fragments. Let's call this data surface an edge data surface. There is also a triangular data surface, a square data surface, a pentagonal data surface, and so on. Well, once we decompress and perform an exclusive OR operation, we can get one of the following type of a result. We can receive an innocent file denoted by Greek letter iota. This is a file where we know every bit and byte of the payload. Typically, this is our declaration of freedom of speech and freedom of file sharing, repeated again and again until it fills up the entire space of the file. Then there is a visible data surface or alpha surface, which is a meaningful file, typically a movie, video game, whatever. The payload of such a file is correctly tagged, which means as soon as the XOR operation is performed, the resulting file contains a recognizable tag at the beginning and at the end of the payload. Then we have an empty data surface, which is a file that does not contain any tags at the beginning and at the end. The content of such a file is a mishmash of random ones and zeros that is meaningless. And finally, a hidden data surface. This surface is very similar to an empty data surface. There are no tags at the beginning and at the end of the payload, but unfortunately, the payload is a meaningful file. One might think most times we cannot distinguish between an empty data surface and a hidden data surface, but this isn't true. Let's go through the logic of low-level sharing rules, which shields users from participating in any traceable illegal activities. First, let's examine the edge data surface. Everybody can see it is impossible to create a meaningful data surface by combining 2 fragments of the same color. On the other hand, it is possible to create an edge data surface composed of 2 fragments of different colors. Such data surfaces should not be shared and must not be used for de-entanglement. Next, we have a triangular data surface. As mentioned before, if the vertices of triangle are fragments of the same color, then the result is not a meaningful file. If fragments of 2 different colors are used, then this is a dangerous combination. Again, such fragments should not be shared and must not be used for entanglement. If the vertices of a triangle are fragments of 3 different colors, then that is quite okay, but I would avoid using such fragments in the entanglement procedure. With triangular data surfaces, we can make one interesting observation. If we know that a triangular data surface is an alpha surface, for example a movie, or an innocent data surface, then we can say with 100% certainty that all 3 edges of such a triangle are empty data surfaces. There is nothing hidden in them. The same rule applies to square data surfaces. If the vertices of a square data surface are of the same color, then the result is not a meaningful file. If fragments of 2 different colors are used, then as you may already know, this is a dangerous situation. Such fragments should not be shared and must not be used in the entanglement procedure. If the vertices of the square are of 3 different colors, then that is quite okay, but we should as well avoid using such fragments in the entanglement procedure. Finally, if the vertices are composed of all 4 colors, then it is a correct data surface whose fragments can be shared and entangled. Now, what observations can we make about square data surfaces? If we know that a square data surface is an innocent data surface or alpha surface, then all internal triangles are empty data surfaces. What can we tell about edges? If we have used 3 fragments where we know they were created properly, and 1 fragment was taken from somebody else, then we can be sure of one thing: all edge data surfaces are empty. If we have used 2 fragments from somebody else, most likely from 2 different users, then there is a theoretical non-zero chance those 2 fragments may contain some meaningful information and those 2 different users are actually one attacker. but the chance of this happening is almost zero. I'm sure you are now wondering, what is this good for? Let's switch roles again. Imagine you are a copyright protector working for a big company like Universal Pictures and you want to attack this peer-to-peer network. The problem is that unlike with traditional client-server topology or when using torrent topology with multidimensional files, you cannot identify who is sharing what. So you cannot easily accuse any user/pirate of sharing copyrighted content or illegal stuff even though you know the IP address of the user. You would need to go case by case to accuse someone and to prove he or she has done something illegal. That is very costly, time-consuming, and your chances of proving it are almost zero. But there is a catch. There is a CCR attack which can theoretically tear this distributed peer-to-peer network into pieces. So, how does it work? Let's assume you have discovered the following set of data surfaces which when assembled will produce a copyrighted work or video game or whatever, and you as a lawyer want to get rid of it. In this setup, we should as well assume each fragment is shared by exactly one computer, which if you think about it, is nonsense. In a real life, hundreds of users will host and share the same fragment. But we will pretend this is not the case. So as a lawyer of some movie producer, you cannot use robots to send DMCA complaints automatically, because people sharing all those fragments are not breaching your copyright. They are individually sharing provable, redistributable nonsense. You would need to involve law enforcement to apply knock and talk strategy, which on its own, even for small user groups, is extremely costly. So, for a brief moment, imagine police going around asking real people questions about those fragments. Let's say they will first visit the person who shares this alpha fragment. Based on your allegations, they will illegally accuse this guy of copyright infringement, and let's imagine that the guy is a naive idiot who really wants to talk to police. First of all, he has no idea if the fragment he is sharing was created during a fission procedure, when somebody was stealing a copyrighted stuff, or if it is a part of Linux distribution which was used during the entanglement procedure. So the guy is honestly innocent. He is sharing a measurable nonsense and he is doing nothing wrong. But, on the other hand, he can also reply that the fragment is a part of the multidimensional file containing the Declaration of Freedom of Speech, and he is sharing it because this is intended purpose of our network. Wink wink, and there is nothing wrong with it. We are just playing funny math game like what the Bitcoin guys are doing, so the law enforcement or copyright protector must go somewhere else. Okay, this time let's try the guy sharing the red fragment. And lo and behold, the same story about innocence comes out. Now let's try this blue guy, and we are back to the same story. Whether you look left or right, whoever you approach, overwhelmingly, people don't talk to you at all, or they really don't know what is going on. And you, as a policeman, have nothing in your hands to prove otherwise. That's it. This entire concept works seamlessly until somebody discovers an edge data surface. Edge data surface changes the situation 180. This is a typical CCR attack, where CCR stands for Causality Chain reaction. If you think about it and ask yourself, what existed first, the blue-white-green triangle or this red-white edge? Undoubtedly, the edge data surface existed before the triangle. There is no other way it could have been done. Therefore, it's clear that the blue and green fragments are tainted, they are guilty if you wish, and the white fragment is innocent. However, perhaps, and I emphasize, there is no case study, no court ruling, and no law on this subject whatsoever. But, perhaps, in the future a court may conclude that such fragments are indeed inherently connected to the copyrighted work and therefore sharing them infringes copyright. So the files will be blacklisted and they will no longer be shared. But what is even more disturbing, from this point you can go on applying the same logic of who is guilty and who is not again and again, which will set off a chain reaction. We could then apply the same rules to this fragment and this fragment and this fragment, etc., etc., finding that all of them are indeed connected to some copyrighted work, and we can do it until we reach a square. The propagation stops here. A square data surface always saves the day. Now, again, it is impossible to tell who is guilty and who is not. That is the main reason why we always use N+2 cores and not N+1 cores. With N+2 core, the CCR attack will not stand a chance. If somebody pulls it off, the damage will be negligible. Users who have multidimensionalized their files in a correct way are practically untouchable. The probability that a user will take into entanglement procedure two fragments created by somebody else, and at the same time these two randomly selected foreign fragments were crafted to trigger CCR attack, is virtually zero. Even if there is such an unlucky user, the application will later detect the situation because it scans blacklists from time to time, and it will repair the corrupted data surface almost instantly. The most important thing is when using N+2 cores, there is no chance to bring the network down using CCR attack. What's more, if we can go back a little and inspect the square/edge causality problem, you can easily see one thing. If the square is created the proper way, then there is no chance anybody can take one of the square vertices and produce a valid, meaningful edge data surface. It is impossible. The only way how this attack could be pulled off is if somebody first created an edge data surface and then used its fragments to produce meaningful square data surfaces, shared those surfaces in the network, waited for a long time till enough users entangled to the poisoned fragments, and then complained. It is a lot of work for minuscule temporary damage, because the application on computers of affected users will detect the corrupted blacklisted fragments and repair the damage in no time. So even if CCR attack is the most promising one, it cannot threaten the distributed data storage.